Today, we're diving into something that could flip our understanding of the entire universe on its head. It's a bold new theory that looks at one of the biggest ideas in cosmology, dark matter, and says, what if it isn't real at all? Right now, the standard story of the cosmos says that about 85% of all the stuff out there is some kind of mysterious, invisible matter we call dark matter. But what if that's just wrong? What if the answer to this huge cosmic puzzle isn't about finding some exotic new particle, but about completely rethinking what we mean by empty space?
So before we can get into this wild new idea, we've got to understand the problem it's trying to solve. Why did scientists even come up with this idea of dark matter to begin with?
Well, it boils down to three major puzzles. First, you've got the dynamics of galaxies. The stars way out on the edges are whipping around so fast they should be flung right out into deep space. The gravity from the stars we can see just isn't strong enough to hold on. Then there's gravitational lensing. We see light from distant objects getting bent around galaxies way more than it should be. It's like there's a much bigger lens there than we can see. And finally, the big one, colliding galaxy clusters. When they smash together, the visible gas clouds crash and slow down, but the source of all that extra gravity just seems to ghost right through.
So you look at all that, and within our current rule book for gravity, Einstein's general relativity, there's really only one conclusion you can draw. To get all that extra gravity, you need a whole lot of extra mass. And since we can't see it, it got the name dark matter. It was the missing piece that made the cosmic math finally add up.
But here's the twist. What if the math wasn't wrong, but our assumptions were? This is where a new idea called dynamic vacuum field theory, or DVFT, steps onto the stage. It suggests we don't need to hunt for a new particle at all. We just need to change how we think about the vacuum of space.
And this slide just lays it out perfectly. On the one hand, you have the standard view. Space is an empty stage, and the extra gravity has to come from a new actor, a new particle. But on the other hand, the DVFT view says, hold on, the stage is an actor. It says the vacuum itself is a physical medium, and all those weird effects we've been blaming on dark matter are actually just properties of space itself.
So what exactly is this dynamic vacuum field? The best way to picture it is to stop thinking of space as this passive, empty box. Instead, imagine it's more like an invisible, dynamic fluid that fills everything. And this fluid, this vacuum, can have its own energy, its own pressure, and that in turn can create gravitational effects all on its own.
Okay, that's a cool concept, but how does it actually work? I mean, how can the vacuum of space create extra gravity exactly where we seem to need it? Well, the theory has a really clever trick up its sleeve.
It's a concept called gravitational slip. Now, stick with me here. In normal physics, the way gravity pulls on, say, a planet, and the way it bends a beam of light are perfectly linked. But DVFT says this vacuum medium can respond differently to matter than it does to light. It's almost like it's stickier for light. This difference, this slip between the two effects, is the theory's secret weapon. It allows you to get extra light bending, or lensing, without needing any extra mass.
And that right there is a game changer. Because if you have this gravitational slip, you can suddenly explain why we see all that extra lensing around galaxies without having to invent a single new particle of dark matter. The effect isn't coming from matter. It's coming from the vacuum.
All right, trying to rewrite the rules of gravity is a pretty big deal, and any new theory that wants to play in this arena has to pass some incredibly strict tests, starting with the one place we've measured gravity with insane precision, right here at home.
I mean, think about it. We've tracked the orbits of planets and guided spacecraft across billions of miles. Our understanding of gravity in the solar system is rock solid. So if your new theory predicts weird effects here, effects we don't see, then it's dead on arrival. It has to match everything we already know.
And this is the number to beat. This is the measurement from NASA's Cassini mission. It looked for this exact gravitational slip effect in our solar system and found, well, nothing. The value is basically 0, with a tiny, tiny margin of error. This number is like a giant cosmic roadblock for any alternative theory of gravity. You have to explain why the slip is so close to 0 here.
So how does DVFT do? It passes with flying colors. The theory has this built-in screening mechanism. The idea is that in really dense, high-gravity places like our solar system, these weird vacuum effects get suppressed, they get smoothed out. So DVFT predicts a slip value of around 10 to the minus 13. That is 100 million times smaller than what Cassini could have even detected. So it not only passes the test, it's completely undetectable here.
Now for the main event.
We're talking about the observation that is always held up as the smoking gun for dark matter, the famous bullet cluster. How on earth does this new theory explain that?
So you've got two totally different stories for the same cosmic car crash. The dark matter story says you have two huge halos of dark matter particles that just pass through each other like ghosts, carrying all the gravity with them. The DVFT story says, nope, it wasn't particles, it was structures within the vacuum's own energy field that passed through each other, and they're what's creating the powerful gravitational lensing.
Let's walk through the DVFT version step by step. First, two clusters are on a collision course. They merge. Second, the gas clouds from each cluster slam into each other and get stuck in the middle, creating that hot, glowing region we see. But, and this is the key, the underlying energy structures in the vacuum itself are essentially collisionless, so they pass right through each other without slowing down. And fourth, it's those passing vacuum structures that create the powerful lensing peaks, which is why the gravity appears to be separated from the visible matter.
And here is the absolute kicker. This isn't just a nice story. The theory makes a prediction you can calculate. When you do the math for the effective mass of this passing vacuum structure, you get a number that's about 200 trillion times the mass of our sun. And guess what? That number is a perfect match for the amount of dark matter the standard model says you need to explain the exact same observation. It works.
So, where does all this leave us? Well, if this theory continues to hold up under scrutiny, it means we could be standing on the verge of a completely new picture of our universe.
This line from the paper really says it all. It basically argues that what we've been inferring as dark matter using general relativity is, in this new picture, just the stress and energy of the vacuum itself. The mystery isn't a missing substance, it's just a property of space that we've been misunderstanding all this time.
And that's really the big question to chew on, isn't it? For decades, we have been building these incredible experiments, digging deep underground, all searching for a new particle. But this theory suggests a fascinating alternative. What if the answer wasn't hidden somewhere out there, but was all around us the entire time, woven into the very fabric of the void? It's a pretty mind-bending thought.